Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Kimi team Kimi K2, a 1 trillion parameter agentic MOE language model. Kimi K2 is a new large language model built with a mixture of experts architecture. Under the hood, it has about 1 trillion total parameters, but only 32 billion are active for any given token, which keeps it efficient. The team trained it on 15.5 trillion tokens, and, importantly, they managed to do this without loss spikes or training collapse. K2 is not just a generic chat model, it's explicitly designed to be good at agentic behavior, like using tools and solving multi-step tasks, and at software engineering. Both the base and instruction-tuned versions are released openly, so others can build on this work. The authors frame Kimi K2 as part of a broader shift in how we think about language models. Instead of just predicting the next token from static text, the goal is agentic intelligence, systems that can perceive their context, plan, reason, and take actions in complex environments. These models should be able to learn new skills by interacting with tools and systems, not just by copying patterns from their training data. Tool use becomes a core capability here, because many real-world problems require calling APIs, querying databases, or controlling software in multi-step workflows. On benchmarks, Kimi K2 is positioned as one of the strongest open-source models that do not use extended chain of thought or long reasoning traces at inference time. On SwiBench Verified, which measures real software bug fixing, it scores about 66, and it also performs very well on the multilingual variant. On Tau2 Bench and AceBench, which stress tool use and agentic behavior, K2 again lands near the top among non-thinking models. It also posts strong scores on coding and math benchmarks like Live Code Bench, AIM 2025, and GPQA Diamond, all without relying on long, slow reasoning modes. Architecturally, Kimi K2 is a sparse mixture of experts transformer. The full model has around 1 trillion parameters, but only about 32 billion are used for each token thanks to expert routing. Typically, 8 experts are activated per token, plus a small set of shared experts that always participate. The team also explores scaling the number of attention heads, finding that increasing heads per layer yields consistent validation loss improvements. Overall, the design aims to push quality while keeping compute and memory usage manageable. Training such a large MOE model is tricky, especially for numerical stability. K2 uses an optimizer called muon clip, which extends the muon optimizer with a new technique called QK clip. The idea is simple. Attention logits, which come from query key dot products, can occasionally explode to very large values and destabilize training. QK clip caps these logits at a chosen threshold, preventing extreme attention peaks. In practice, this allowed the team to pre-train on 15.5 trillion tokens without any loss spikes. Small-scale experiments with aggressive clipping show almost no degradation in loss, suggesting that QK clip is a safe way to constrain attention. When you look at the training curve for Kimi K2, the loss stays smooth throughout the entire run. There are no sudden spikes or collapses, even though the model is huge and the training is long. This is strong evidence that the combination of muon clip and QK clip is doing its job, keeping attention numerics under control and allowing stable optimization. That stability is a key enabler for scaling up mixture of experts models to the trillion parameter regime. The authors also study how architectural choices scale. For sparsity, they fix the number of activated experts and shared experts, then increase the total number of experts. This effectively increases sparsity, and they observe that performance improves as sparsity grows, up to their tested range. Separately, they compare models with a baseline number of attention heads to versions where the number of heads is doubled. Across sizes, doubling heads consistently reduces validation loss by about 0.5% to a bit over 1%. These trends guide the final K2 design toward more experts and richer attention. Handling very long inputs is another practical challenge. K2 uses a chunk-wise, autoregressive rephrasing pipeline. Long passages are split into smaller, overlapping chunks that preserve context. The model then rewrites each chunk in sequence, using the previous rewritten text as context, and finally stitches the outputs together. This approach lets the model clean up or normalize long inputs while staying within context limits, and it improves downstream instruction following and reasoning on lengthy documents. A central contribution of this work is the large-scale data pipeline for teaching Kimi K2 to use tools. The pipeline starts by building a massive repository of tools, both real and synthetic. Then it generates agents and tasks tailored to different tool sets, and finally simulates multi-turn trajectories where agents call tools, observe results, and refine their actions. A separate judge model filters these trajectories for quality. This pipeline produces tens of thousands of diverse, high-quality examples that train K2 to behave like a capable software agent in complex environments. The first stage is to assemble a rich tool repository. The team pulls over 3,000 real NCP tools from GitHub, which come with well-defined specifications. On top of that, they generate more than 20,000 synthetic tools using a hierarchical domain evolution process. They start from broad categories like financial trading, robot control, or software applications, then refine into specific domains and synthesize tools with clear APIs and behaviors. When they visualize these tools with t-SNE, real and synthetic tools occupy complementary regions, indicating broad coverage of the tool space. Next, they generate a large population of agents. Each agent is defined by a system prompt that encodes its persona, expertise, and behavior, and by the specific tools it can access. For each agent configuration, they create tasks that vary in difficulty, from straightforward calls to multi-step workflows. Crucially, every task comes with a rubric, a structured description of what counts as success, what tool use patterns are expected, and how to evaluate intermediate steps. These rubrics make it possible to automatically judge whether an agent's trajectory is correct and high quality. In the final stage, the system actually simulates interactions. User personas generated by language models initiate tasks with different communication styles. Agents respond by planning and calling tools through a tool simulator, receiving observations and adjusting their actions. This produces full trajectories, a sequence of messages, tool calls, results, and reasoning steps. A separate judge model then evaluates these trajectories against the rubrics, filtering out low-quality or incorrect ones. The result is a large, curated dataset that teaches Kimi K2 how to use tools effectively in realistic, multi-turn scenarios. To better understand their tool collection, the authors embed each tool into a vector space based on its specification and behavior, then visualize these embeddings with t-SNE. Real MCP tools naturally cluster according to their original categories, like databases, cloud platforms, or media processing. Synthetic tools, generated by the domain evolution process, occupy structured regions corresponding to predefined domains, such as healthcare, industrial IoT, or education. Together, these two sets cover a wide range of functionalities, which should help Kimi K2 generalize to new tools and tasks it hasn't seen before. After pre-training, Kimi K2 goes through an extensive post-training pipeline. The team builds a large instruction tuning dataset that spans many domains, using a mix of human annotation, prompt engineering, and responses from strong expert models like K1.5 and other in-house systems. Automated judges, sometimes backed by humans, filter these responses for quality. Beyond supervised fine-tuning, K2 is further improved with a joint reinforcement learning stage, where it interacts with both real and simulated environments. This RL phase is particularly aimed at sharpening agentic behavior, coding ability, and multi-step reasoning. When you line up Kimi K2 against other leading models, both open and closed, it holds its own. On many benchmarks, it's competitive with proprietary systems like GPT 4.1, Claude 4, and Gemini 2.5 Flash. Among open-source models that don't use extended chain of thought at inference time, K2 is often at or near state-of-the-art, especially on software engineering and tool use benchmarks like SWE-bench and TileBench. Its math and STEM scores are also strong, suggesting that the model balances broad general capabilities with deep agentic and coding skills. Because Kimi K2 is designed to act in complex environments and use tools, safety is a central concern. The authors report a dedicated safety evaluation suite that probes for harmful content, misuse of tools, and other risky behaviors. Safety filters are applied during data collection and post-training, and agentic behaviors are monitored and constrained to reduce the chance of dangerous actions. The team treats safety as an ongoing process, refining both the model and the evaluation protocols as new risks and use cases emerge. To wrap up, Kimi K2 shows how to push mixture of experts models to the trillion-parameter scale, while keeping training stable, thanks to innovations like Muon Clip and QK Clip. It also demonstrates the power of large-scale, synthetic tool use data for building genuinely agentic language models that can plan, act, and solve complex tasks. With strong performance in software engineering, math, and tool use, and with open checkpoints available, K2 is positioned as both a practical system and a research platform for the next generation of agentic intelligence.